All right, we already talked about geometric sequence and series. Now I want to talk about what happens when you use geometric series and you don't stop, you just go to infinity. As a prequel to that, let's talk briefly about what happens with arithmetic series if you go to infinity. If you go to infinity with arithmetic, like 1 plus 3 plus 5 plus 7 plus 9 plus, as I take the limit as that approaches infinity, it's pretty obviously I'm going to infinity. And even so, when I talk about power 1, 2, 4, 8 geometric, that goes to infinity. But this series here is part of a famous puzzle. Where does that go? To explain, I'll give you the riddle. Let's say you're trying to walk across the forest. And every day you decide to walk halfway to the other side. What day do you get to the other side? Even if you're only an inch away, going half the distance is only going to let you go half an inch. You can't get out. It's not possible. And so all of this, half a forest plus a quarter of a forest plus an eighth of a forest plus a 16th of a forest plus a 32nd forest plus a 64th forest, is not going to add up to 1. As you get closer to infinity, you get closer to 1, but you're never, ever, ever going to make it to 1 until you make it to infinity. So, what's different between these two? And the answer is, what is the ratio? In this case, the ratio is 2. In this case, the ratio is 1/2. Why that's significant is because, as you know, the sum of an infinite series is, sum of a geometric series is a1 minus a1 r to the n all over 1 minus r. When r is 2, and I go to infinity, 2 to the infinity is, well, infinity. And infinity times a1 minus negative becomes, this whole thing becomes infinity. But when I take a sum and I use a half instead, something bizarre happens. If I rewrite this as, let me get a little more, well, let's do the room in this quarter. a1 minus a1, 1 over 2 to the infinity. Well, we know what that does. That becomes 1 over a really big number, which is 0. Which is infinity. And 1 over really big becomes 0. This goes to 0 as I approach infinity. And if that becomes 0, then this whole thing becomes 0. And I end up with the sum being equal to a1 over 1 minus r. So, to paraphrase, an arithmetic series always blows up, goes to infinity. If, on the other hand, our a common ratio for a geometric series is greater than 1, notice the absolute value bars, is greater than 1 or equal to 1, then this thing goes to infinity. If, on the other hand, the ratio is less than 1, actually I should back this up. Well, it says it's on the worksheet, but it's not true. It's when it's greater than 1, it goes to infinity. When it's less than 1, it goes to a number. And we can say that the sum is equal to the first term divided by 1 minus r. Fair enough? And so I can take a series, like for example, the example, which starts off with 3 over 2 minus 3 over 8 plus 3 over 32 plus dot, dot, dot. I'm going to infinity. I look at this thing, the first thing I would say is the ratio. How do I find the ratio? We do negative 3/8 over 3 halves. And I get, flip and multiply, I get negative 1/4. I note if I multiply this by negative 1/4, I get the next term in the series. And so I know the ratio is negative 1/4. Is that absolute value of that less than 1? Answer, yeah. So this is my sum. So then I go my sum for the infinite series is equal to the first term, which in this case is 3 halves, divided by, got a random minus sign there, let me get rid of that, 1 minus negative 1/4. And so I get it's 3 halves, 1 plus 1/4, and that would be 3 halves over 5/4. Flip and multiply, I get 3 halves times 4/5, and I get 6/5. Is that right? That's right. That's what I get, 6/5. And that's what I'm approaching as I go to infinity. Fair enough? Fair enough. This also leads to another kind of funky thing that happens on the way. If I have 0.765 or 762, and I go to do the problem, it's a repeating function, right? So it's 0.762, 762, 762 forever, right? If I were to look at the first 3 numbers, I could rewrite that as 762 over 1,000 plus 762, well, this would have to be over 1,000,000, right? I'm going to pause there because a bunch of you are like, what just happened there? So hold on. Got it? All right, because this is, if I just ignore this first part, I ignore this first part, this part here, I ignore that first part, and this is 762 over 1,000,000. Plus, I could add 762 over, this would be billions, right? Over 1,000,000,000. Well, look what I've got here. I've got a geometric series. What's the ratio? I'm multiplying by 1 over 1,000 to get the next term. Is that less than 1? Absolutely. Since it's less than 1, what I can do is I can write this as the sum of the infinite series, which is an infinite series because it's repeating forever, is equal to a1 over 1 minus r, which is equal to 762 over 1,000 divided by 1 minus 1 over 1,000. That would be 762 over 1,000 times, flip, actually let's do this, let's do the fraction in an obvious way. So I got 762 over 1,000 over 1,000 minus 1 over 1,000, and that's going to give me 762 over 1,000 over 999 over 1,000 equals 762 over 1,000 times 1,000 over 999, flip and multiply, and I get 762 over 999, which, by the way, can be simplified, I think. Yep, I can. Divide top and bottom by 3. Let's bring it over here because I'm like really low right now. So that would be, divide top and bottom by 3. I get, the bottom is 333. The top would be 762 divided by 3 would be 254. I see nothing else that comes out, so I'm there. Terrible writing. Well, let's try this again. 254 divided by 333. Got it? All right, that should get you started so you can do the problems. Go ahead and try the problems on the back, and we will talk.